All right, what's up everyone? Welcome to week 61 of Chill Kernel Hacking for Fun. Thanks for joining. Let me get set up. So today, like we have been doing for a minute, we are continuing to work on the network driver. And we made a lot of progress last time. We actually got transmits to work. So yeah, we're gonna, holy crap, Afnan with the test 0. Test 1. What's up, Afnan? Afnan, super punctual today. Word. And maybe check out Twitch. Yeah, so network driver stuff for it, so yeah, on time. Yeah, so last time we got this part working. So we're gonna go over that. I'll show you the progress we made there, and then we're gonna move forward. I still need a minute to open my documentation and stuff. We need the E1000 manual. Got our handy E1000 manual. We need our Miro. Okay. Miro loaded up. Okay. Miro loaded up. Hope everyone's having a nice Sunday. Today's the 30th. Here with episode 61. All right. All right. What else? What else? What else? Soundboard check.
This is a certified hood classic.
I got some new sounds today, actually.
Man, this crunk, come on. Haters gonna hate. Sheesh. Brutal.
Some new sounds for today. Eardrum went kaboom. Oh man, sorry about that. I thought it wasn't super loud. Thanks for letting me know. My bad. Okay. What else do we need? All right, let's start off by checking the diff. See what's going on. So all that really happened was temp, it's working. So here's the basic driver. None of this matters. Single transmit, and crucially, the panic is commented out. Even if you're on max volume, this stream should not be dangerous to listen to, so that's my bad. I will.
Brutal. Brutal.
Yeah. So basically all of this was working correctly, actually. The key issue was that we had this panic that was a little bit too close to the transmit. That's right here. After we initialized, we did a transmit. The panic was too close and it didn't work. And now I've added a few more. I'm just gonna run. So I'm going to delete the PCAP. So we have no kimu.pcap here. I'll run kimu, which took kind of a long time. And now we see kimu.pcap. We can TCP dump that thing, and we can see a bunch of data is in the pcap file. Which means that we're sending some data out, so that's pretty good. There's a few things we can do from here. Test wrap around. If we exceed the 32 descriptors in the ring buffer. That's so far it's untested. Technically, there's also the second part about correctly checking if the ring buffer is full via using DD rather than reading the head register. So the problem was that apparently reading the head register causes some race conditions, and there's a different way of doing this that involves rather than checking if you want to see if the ring buffer is full, rather than checking rather than reading the head pointer and comparing it to where the tail pointer is, you instead use this feature of the NIC where it will write certain status bits into the descriptor when a packet has been sent. And so you can use these to determine if the queue is full. At least that's my understanding. So I'm just going to go ahead and clean the code up a little bit. Things are getting a little bit too messy for my tastes. So we'll actually want to do this later. This is commented out. It's okay. Yeah, okay. This panic needs to go. So with the panic is now it's in init.c. We have a panic after PCI init. So we kind of stop there instead of going and running some random user space code. I'm going to delete this. Just clean stuff up. This hex dump function doesn't really belong here. This was all for debugging. Yeah. All right. So that's still working good. I think in the end, this is all going to kind of get squashed into one commit. Temp cleanups. Hack, blah, blah, blah. This is all going to get squashed, I think. Yeah. Let's do this. Let's first fix, so going back to our plan for a few things to do. First, let's fix this And then let's do this. So we're going to do it in this order. So first we're going to correctly check if the ring buffer is full using the DD bit. And that means, sup, Udaya, some type about drivers don't support. I mean, I'm sorry, I totally don't understand the question. I'm also not sure I can even answer that. Yeah, so going back to sort of I'm just going to do it rather than talking about it. So what we need to do is we need to initialize init dd bit for every descriptor, right? And just to quote the manual on that. All right, so going back to the manual, here's the part where it says to don't read the head pointer that is racy. It says instead set the RS bit and then check the transmit descriptor DD bit because of some reasons. So what we're going to do is on initialization, we set the DD, and this is like to do don't just use a 1, but the DD bit happens to be where is the screenshot? The DD bit happens to be bit 1, transmit descriptor. So we have the commands and specifically with the status. So in the descriptor, we have, okay, no, that's actually the, this is the whole thing. This is the whole descriptor. Within the descriptor, we have a command, a status, and that's basically what we care about. The command is the thing that lets us set the RS bit, which opts us into this whole DD report status thing. So we're setting that bit. And then software does it by looking at the descriptor status byte and checking the descriptor done DD bit. Status byte done DD bit, and that is this thing. So what we're going to do is set the DD bit on everything, which kind of will make the ring buffer look empty, basically, as if the NIC has processed all these descriptors and they are now available. And then what we're going to do is we're not going to read the head because that's racy. We're just going to see if, maybe going back to a visual of this, let's copy this over here. All right, so our head and our tail, and we're pushing stuff all the way along. And basically the simple condition is if the tail is pointing at a descriptor that is available, meaning the DD bit is set, we can use it and increment the tail. And so let's just take it from the start. So let's say the buffer is empty or initialized, which means head's going to be at some place by the start. Tail will also be pointing there. all of these are initialized to empty with the DD bit. Then on the first push, we basically, on every push, we just look at the tail, look at what it points to, see is the DD bit set? If it's set, that means the hardware has processed the packet, and which means it's available now. And so we can populate the descriptor and then advance tail and just bump it along. And let's say that the hardware just like hangs for a long time and doesn't process anything. Then eventually we will fill up the whole thing. It's maybe a bit easier to see with the wraparound, but let's say the head's here and we're pushing everything. And we even push here, tail, let's say tail is right here. Screenshot this so I can have something, let's say tail is right here. Okay, it's these still have the DD bits set, so they're available, so we populate it, push it here. This is the last slot. And according to the simple logic I'm proposing, we can just actually use this. And what's going to happen is actually these things are going to point together now. If we actually do this, theoretically, they would actually point to be the same. And if an observer is actually trying to detect fullness by comparing these, the buffer will actually look empty. So that sounds like it could be bad, but I'm actually thinking it's not going to be a problem in practice, because in practice, there is no observer that is going to do that comparison. All decisions about the state of the buffer being full or empty depend on the DD bit, basically. And so even if this happens, and we completely push the full buffer to the point where these two things point at the same thing, and the hardware's like frozen, the DD bit will be empty, because on every time we populate a buffer and push the tail, we clear the DD bit. So therefore, we get to this position. Let's say our software is trying to push another packet. We're going to look at the tail, see that the DD bit is 0, and we're going to not do anything. We're going to drop the data or whatever we're going to do. So I think that's fine from the software's point of view. We're never actually comparing the head versus the tail. From the hardware's point of view, all it cares about is this head pointer and what's there. And so it's also not doing this comparison if the head and tail are equal also. All it does is it looks at the head and sees, is the head pointing to a descriptor that So maybe I'm wrong about that, but I believe the hardware's, no, I should look at the manual and see if I can, it's like kind of a lot of information to read though. Packet transmission. Okay, to be honest, I'm not actually totally sure what the hardware really does, but I have reason to believe that this method of doing this is correct because some other OSs do it this way. For example, I was looking at the XV6 2022, and basically this is kind of what they do also. They initialize the buffer to DD, and then they don't actually provide a complete transmit, but the fact that they do this strongly hints that that's what you should do. So I'm just going to stop talking and actually just code this. So we get the tail and we get the descriptor. And before we do anything, we look at the descriptor and see if it's free. And maybe, I hope AI doesn't suggest something for me right now, but we need to check if the DD bit is set. And so if descriptor status and 1, basically, then I don't know, we chose this return to thing. I am going to actually disable configure code completions. Disable completions. Okay, it seems like it's disabled. To do check DD bit, but basically it is yeah, if it is free, so if it is if the bit is set, that means it is free. So we're going to do a not. So, and I wonder, is there some DD? Function D. Okay. What is this? This is not right. Stat DD. Stat DD. Something like this. This is this one constant. It's a little bit not in the format that I need because it's like this full 32-bit integer looking thing. And in fact, this constant, this status is actually an 8-bit, or it's actually it's actually just a 4-bit value, but I think that should be fine. Then we drop the transition. Otherwise, okay. Just double checking that. So is that right? So if the bit is set, it is not set. And we want, so otherwise the bit is set, and we do a few things. First, we mem set the descriptor. We find the backing buffer and copy our data into it. And then we set a pointer. In fact, this is like actually kind of redundant. In the current way this works, each descriptor correlates 1-to-1 with a piece of the backing buffer. So we don't actually need to really do this, but the simplest thing to do is just clear out the whole thing and rewrite all the fields. And to do use constants instead of these hardcoded things. And this is setting a few bits. This is setting the end of packet bit and also the RS bit. So going back here, so we said that here. So we have a few bits, and we want the RS bit, that's the important one. So we have bits 0 and 3. Yo, what's up, KR Codes? Hello. Also, what's up? I just see we got some Twitch. We had some Twitch viewers in the chat. Sikar and Wow Tech came here for the first time loving this. Wow, thanks. Finally, the real programmer are using the stud sit or your own implementation. I actually, I'm not sure. I think it's the one. I think it is actually provided by the compiler. So for context, I'm following this OS coursework, so I didn't write a lot of this code. But I actually think that these core functions are provided by the compiler. Maybe that is actually a question for an AI tool. Does a C compiler automatically provide definitions of mem copy? No. So maybe I'm wrong. I was kind of under the impression that in some cases, the compiler provides implementations, but I don't actually see any. Oh, but maybe I'm not looking hard enough. String.c. Okay, so these are, nope, you're right. They are just sitting here. Very basic ones, I think. Yeah. Although apparently they actually do some optimizations for x86. So yeah, that's not really what I'm interested in. Thanks for asking. Yeah, I'm actually trying to avoid doing as much of that work as I can because I don't find it super interesting. Okay, but basically this is like the super simple change, and we are now using the DD bit to tell if we can push or not, basically as the sentinel for whether the buffer is full. And nothing should have changed. This is actually kind of interesting that this hello. So this is my print that I've added to Kimu, and it just kind of like fires sometimes. And it just like fires sometimes. Ah, interesting. And so we see some Ethernet frames that I have transmitted from my OS, but we also see some random other network traffic, and this actually looks well formed. And I actually think this is traffic from other parts of the virtual network that Kimu creates. We saw earlier that when you use Kimu's networking, it creates a virtual network with other like servers on it, and I think those servers, like a DHCP server, for example, and those other servers broadcast packets sometimes. So that's what we actually see, which is kind of interesting. Yeah. Subsikar, are you following a source? Yes, I'm following this. I wonder if my Twitch commands, my Streamlabs commands work in Twitch too. I'm following this coursework from MIT. So let's just do another basic check that everything still works. I fully expect it to. Okay, wait, but actually no, it doesn't work. It stopped working. Is ETX disabled every time now? What is going on? This is... Okay, there weren't that many changes. Okay. I am kind of confused actually, so I'm just going to quickly revert the change manually. which is pretty easy. All I need to do is this. I did change the ordering there, but that should not matter. And like I uncommented this. So what happened there? So that like is fully working. And if so if I re-enable that, that should actually be benign. And capture one, so that's working. So it's something here that I did. And probably the answer. No, maybe I think I was being stupid, I think. So if the bit is set, it's free. That's wait, no, so I was right. So wait a sec. If the bit is set, it's free. So the bit is not set, it's not free. So I'm just going to do a basic print there. But something very strange is happening actually now. It looks like so we're initting several NIC devices. What's up, Corey Bot? Long time no see. All right, dang, it looks like the Twitch command did not work. Does this even run? So, okay, so something. Oh. Okay, I think my comparison is maybe wrong here. I'm just going to quickly flip it around. So if status and 1, for example, then let's do all this stuff. This is kind of, I think I need to go back to C school and learn how to do my bit operations. So this is like a bit, this is just like, I think, okay, maybe this didn't work. I'm still not sure actually. This is the ultra basic version of this. If the 1 bit is set, we do all the stuff. Otherwise, we don't. What is the status? We're all printing. It's desk. Status is 0. So that means that, is this? Oh wait, no. That's why. I'm initializing this wrong. I'm trying to write to the status bits, not the command bits. That's stupid. Okay. Great. That looks much better. JV, what's up? What's up, JV? All right. Man, I thought I was going crazy. Okay, so we initialized the status bit to 1. And now we should be free to do this a bit better. Yeah, that's still working. Okay. So we have the basic operation working, right? Let's just remove this. Quickly do a double check on that. And Wireshark this guy. So we see what we expect to see. It's for 4 Ethernet frames, which each correspond to one of these 4 transmits that we're doing, and we're transmitting a buffer of 128 bytes. It's all zeros except for the first byte, which is 44, and that's what we see in Wireshark. 44, then all the rest of these are zeros, and it's simple 4 of these. So that's the most basic data transmission we can do. Okay. I'm going to get rid of this thing. All right. And this all looks okay. So it's time for a quick checkpoint for it to use DD. Okay, and next up I want to test what happens when we try to send more than 32. Yeah, like packets basically, because currently we're not testing the wraparound functionality. Here's where I think the emulation will differ a lot from how the hardware works, because I think the execution here is fairly synchronous. When we write to the TD, the tail register, if we go to the QEMU source code, QEMU pretty much immediately reacts to this and triggers this start transmit function, which I think is going to synchronously actually, you know, it does actually do this check. So my initial assumption that actually the hardware is not doing this check is wrong too. So I actually don't have full understanding of how the buffer full detection works, because in the worst case, this thing goes all the way around. And in the worst case, and the hardware's just sitting there, we even push to this level. In which case, if the hardware then kind of like asynchronously comes to life and tries to process this, if it's doing something like QEMU, it's going to not do anything. So it is actually possible that we still need that for the full check, we cannot just simply naively kind of push this to make them equal. I guess what we need to do is check if check the state of the next bits here, actually. So basically everything is going to be 0. The DD bit will be 0 all the way here, but it's going to be 1s for these. And then we're here, let's say we're here, we see that the current one is available. Maybe also the next one is available too. And then therefore we push it this far. But we probably should maybe still stop here. So the check needs to be, okay, we see that the tail points to a descriptor with DD bits of 1, which means the descriptor is available, but we also need to check the next one. So that's what I'm going to actually do. So what we need to do is okay, so we need to wrap index uint 32t this, like, after, like, descriptor, it's basically like tail plus 1 is what I want to do. What's the name? I'll just do tail next equals wrap index tail. Wrap index is my super simple modulo function. And now I'm going to look at the descriptors for both of these. And then the check is bool is full equals, and that's going to be, first off, is or script next status does not have DD. They both need to have DD, basically. Actually, no, this is like actually is empty. So if is no. You know, this is full. If either the one we point to, this one, does not have the DD bit, or the next one does not have the DD bit, then that's this specific condition where, for example, there's like white stuff weirdly in here, or in here also. So like in case we're here specifically, it should actually not be possible for these to be equal. Maybe we could put an assert there, but for this specific case, we do not want to push another one, which reduces the kind of the size of the buffer to like 31 instead of 32. Okay, so then if is full descriptor free. Technically, I think, so tail, under proper circumstances, tail, under the first case, tail points to an empty one. Tail should always point to an empty one, basically. It's just that tail next could possibly point to a contained one. We could even maybe make that an assertion. We could even assert, because it's really all about so assert that desk status and DD. Right. So then is full basically just becomes, is the next one, is the DD bit not set on the next one? Okay, and we just do this as full check. So now let's try this. It looks like it worked. We have the 4 frames that each start with a D. So that is going. Okay. I think I'm going to keep it like this. So now what I want to do, and I'll also make a quick commit, properly handle full buffer. So now what I want to do is actually do a bunch of these. I'm going to do this in a loop for int I equals I less than 2 times k num tx descriptors I plus plus, and what I'm just going to do is a bunch of transmits, and for each one I'm just going to actually use I as the first byte here. And this is just to make sure that transmission can support more than 32 basically, because 32 is the size of our ring buffer, and so this is kind of just checking the wraparound. Let's see. So right, so what should the last number be? KTX numbers descriptors is 32, so we should see 64, and hex 64 is what? Hex 40, right? So the last one should be hex 3F, yep. So that seems to be working okay to me. We transmitted 64 packets on the NIC. Which is sort of telling me that it's kind of working. Although I think it doesn't actually say too much because we're running in QEMU, and we're actually not really exercising this asynchronous nature of the hardware, where it's asynchronously handling data. This is just totally synchronous. Like, we issue a write QEMU, and literally in that moment, we're kind of blocking, and QEMU is handling this and sending a packet out and advancing the head pointer to the next one. But in theory, I think it maybe could work for maybe actual hardware also. Okay, making good progress today. I think it's time to let's just take a quick 20 seconds, stand up and stretch. I'll be right back. All right, I'm gonna call this a win so far. So I'm gonna trigger some of these sounds. Hopefully it's not too loud. Okay, I'll see the music stopped. What is going on there? All right. And so what's up, Luis Keita on Twitch?
This is a certified hood classic.
Yeah, okay. Nice. Useless, what's up? What is up? I see. All right. I just realized my camera is a little bit cutting off my head today. All right, fix that. How old am I? I am in my 30s. Okay. Let's keep going. What's next? So we did these kind of first two things that I wanted to do today. We correctly checked the ring buffer and we tested the wraparound. Yeah. So now we're here and we could just use this thing that everyone else is using. Even though it's kind of a poor fit. No, maybe it's actually, it's like kind of a large number, like it's like a full integer, but I think that totally works here. So. I think this is working totally perfectly, or well enough. Okay. How can we improve this? It's a little bit obnoxious to write the registers via this extremely verbose thing. So we could tweak that a little bit, but in general, I don't want to be tweaking stuff so much. I'm trying to just make progress. We can delete this whole paragraph. We can maybe improve some of the naming here. And what can we call this? This is oops. Tail. Descriptor. Tail next. Descriptor. This does not need to be formatted like this. This doesn't need to be here. Is full check happens. Okay, we should use some constants here. So txrs maybe. But here's where things don't work, because this is where it starts to use this weird, extremely high constant, as if like for the, yeah. So I'm instead going to define my own constant, which I guess I'll just do at the top. The naming is always kind of weird here. I just need a 3 though. And then I need a 0 for something else. This is, I'll just call it E1000 command EOP, right? And then this will be command RS. E1000 command RS. Wait a sec. But that's the shifting thing. That's not exactly what I want. Command EOP is actually 0, but okay, so it's 8-bit thing. So 0 and 8. So then here I can just, this I can just simply do command rs e1000 command eop. And it's, I think it's technically not right to always be using the EOP. That's the end of packet bit. Let me just, what's up, electric machine drives? Yo, got a lot of people on Twitch today. That's cool. What's up, Hawkman? Can you tell me what you got to do in this lab? Like what part of the kernel? Totally, yeah. So here we are working on the network driver. So it's a driver for an Intel E1000 network interface card. And so the goal is to initialize the hardware and be able to send and receive packets using it. And so far I've been just working on the transmit sending part of it. And I finally got that to work. Just now. Maybe I can even just do something like this to make it even a bit clearer. Okay. This should all totally be working still. And we get all these packets. We get hex 40 transmissions. So that is still working. So we're still good. I might also rename this MIO status. Oh, did I not even use, wait, what? Oh, we're not even using that thing anymore. We're just using the E1000 status. Okay. Awesome, we can clean this up. We have our global driver. And why is this global again? Like, why is this structure definition global? Is this used? Oh, it's used in these function declarations. Actually, so we don't need to actually expose that. I think we can actually just have a forward declaration. Let's comment this out. Bring this over back over here. Yeah, so I think that also totally works. Make unknown type, damn. How to do, isn't this how to do forward decla in C? Am I? Unknown type name. Oh, maybe it's this type def struct thing. So type def. Okay, okay, I see. In C++, you could just do this. I have a struct e1000 driver. I want to forward declare it and then prototypes later in the header can simply use e1000 driver instead of also saying struct. How to do this? Okay. So you need 2 of these? Is that how that works? But I think conflicting types. Okay, this got way more complicated than I was hoping for. Okay, forget this. We're ditching all. We're just going back to declaring the struct here. Okay, good. Close. What's this thing for again? Is this unused? I think this is like some global pointer. I think it's totally unused. Okay. We have our descriptor structure, which again, actually, who is referring to this? Also, why does it say no one is referring to this? We have, I think the structure definition does not need to be in the header. But I'm kind of micro-optimizing here. None of this really matters to make progress here. So I'm just kind of being OCD. So this is a bit of a to-do. Drop the data. This exit thing doesn't really belong here, but that doesn't really matter. Okay, I think I can also actually kind of comment out this test transmit. We don't really want to be doing this in the init. Okay, so now I feel like this is looking pretty good. And we can go and squash all of this into one commit and then reword it. This does kind of 2 things at once actually, but I'll just actually, you know what, did not exactly mean to do this. So this is the nick, and then this is actually where I want to do its working part is for the transmit, I believe. Yeah. Okay. And basic transmit. Then this one is implement basic nick initialization. Okay. Technically, I guess there's a couple things in here that don't. So this, actually, I guess this part, this hunk, and some of this stuff doesn't need to be here. Okay, anyway, not really worth it. Cool. Checking the chat. All right. I think we can move on at this point. Let's keep it moving. So exercise 7, add a system call. That lets you transmit packets from user space. The exact interface is up to you. Don't forget any pointers to check any pointers passed to the kernel from user space. Right, so time to add a system call. And what could this look like? I guess to maybe even start off, I should just have a basic user space program that I can use for testing some of this stuff. So I'm going to remove my panic and user.c. Where's icode.c? I'm just going to return. I'm just going to return. I'm just going to, I don't even know what this does, but I'm just going to running. And what happens here? Blah, 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 blah. Running, here we go. So the user space program runs, it does its thing, then it exits. I'm not really sure, okay. So we have a couple of user space processes. We have the file system server is still a thing. That's here. We have a few user space processes. We might even have the other one, this network service thing. I'm going to also disable that for now. Was it test no ns? And then C Linux. Okay, so now this is a bit more minimal. But we have our user space program. Unfortunately, we still have the file system server. I'm going to disable that also. So now we have a more quiet environment. It's just the simple program running. And now we can use this as kind of our user space playground. We need to add a system call. Add system call for transmitting data from user space. And how might this look? What's the simplest version of this possible? We have a system call. 20-second break. All right, be right back. So what is it saying to do exactly? It is saying so we're just basically exposing this raw transmit ability to user space, I guess. It's a very like unprocessed network transmit. So it could be something as simple as int. Maybe it's better if I have an actual text box here. Int I don't know, network transmit or something weird like that. Because this is not, it's like very far from a full socket API. At a minimum, it just takes in a buffer and a length, and then has some kind of error output, presumably. It's just funny how kind of simple this is, like, and naive this is. It's just like, there's nothing about setting up connections or anything like this. It's just like really like send something out of the NIC. That is the most minimal version of this thing possible, I think. So let's experiment with what this would even look like, just playing around. So if we go to syscall.c, I really wish my auto like jumping around would work. Why can I not jump to definition here? Okay, all the other syscalls are here, so I will just sys network transmit, something kind of simple like that. Maybe uint 8t, buffer size t, length. Right. And really, to just do this, we're going to need to include the e1000.h here, which you do like this, I guess. Not the greatest form, just be directly this. I like to be including this stuff so directly. Submit. So, and if we include that header file, we get access to the all-important E1000 transmits. But we need to pass this driver. And that's kind of the unfortunate part, because it's actually, it was declared privately here, so this is just a bit of software engineering work I'm not sure about, but like, what is the best design for how to do this? I'm not sure. For the moment, I will just do it like this. G E1000 buffer len, and that's a const AT buffer. Also call that a const len. Return. Does this compile? No. This thing is a char, so okay. Well, for the moment, I'll just make this char, just to move forward. And that multiple definitions of G1000. Oh, this we are missing. Okay, wait. This thing got included into multiple definition of G1000. I see. I guess that's where we need the extern. This thing comes back here. At least that's how I hope it works. Yeah, that compiled. Okay. So this is just the simplest, like rawest syscall we can possibly do that exposes this very primitive functionality to user space. In terms of the implementation, there's a lot of constraints actually. So currently you are constrained with how much data you can send. That's kind of important. So all of this will probably need to change. But right now you are kind of severely limited to transmitting things in 128 byte buffers. Probably not ideal, like probably not an ideal user interface. So at some point there should probably be some layer here that either like breaks up a larger buffer, transmit into multiple sub buffers. Also potentially dynamically resizing this backing buffer to accommodate larger buffers. Yeah, it's all possible. Yeah, I guess there's a lot of different ways to go here, but I think for the moment I'll just keep it simple like this. And what happens on failure? Like if the thing is full, we just simply drop the data. Okay, so I'm just going to take a note of some of these. Okay, so currently transmit sizes are severely limited. Static 128 byte blocks. Need some layer to take larger buffers and emit multiple transmit calls, if so. For example, we could do that here in this system call. We receive an arbitrary buffer, and we just do our best to loop through it in suitable increments to transmit the whole thing. My question actually is about this end of packet bit. I want to go back here and just do and re-enable that test, but also I'm going to disable this EOP thing. My guess is that actually we're just going to see one enormous Ethernet frame, potentially. Not sure what's going to happen, but let's try. So it looks like Kimu did not actually write anything. It waits for the end of packet bit. That's actually really important. So if you do transmits, you need to be able to specify whether it's an end of packet or not. it's kind of a limitation where currently just everything is immediately flushed out as its own packet. I actually think that needs to be able to be specified by the caller. The caller should be able to pass at least of this pretty low level function. Bool is end of packet. Oh, didn't work. And yeah, so then I don't know, something like this is end of packet. Oh. Packet, then this, otherwise 0, for example. And then now every caller is broken. Also, this thing is broken. So now, I don't know actually why we don't need this anymore, because the prototype is in the header file. And now we can go to the transmit here, and we say false for all of them. And then we can just do like a cute little, I don't know, 1 true or something like that. Or what we can do is, now let's just do it this way. So I don't know what's going to happen here, but here we send a bunch of stuff without the end of packet bit, and then at the very end we just send a single thing with that bit sent. And my syscall thing is not compiling now. I'm just going to say true here. And now we see that Kimu wrote some stuff to disk. And let's check out what it is. And it seems to be how I expected it. It's one massive Ethernet frame. And every so often we see the incrementing index number until maybe the end where we see 3F and then a single 41. So that kind of clears up how that works. So it's good that we have this argument. And I'm just going to say that that user space probably wants to send arbitrary, semi-arbitrary packet buffer sizes. At least not be constrained by the 128 thing. So we have a couple options to solve the 128 thing. One option would be to take some larger thing and emit multiple transmit calls. Also, alternatively, we could use more sophisticated memory management for the descriptor buffers, or even just make things a lot bigger. So currently we're using just a bunch of very simple pre-allocated buffers. It's just like 1 page of data that's reserved for this. Yeah, it's pretty simple. Nothing is preventing us from using more except overall memory limits. I'm not entirely sure. Really, what's the best solution there? Like, we probably could dynamically allocate stuff. you know, instead of, it would basically affect here. So here's where we get a backing buffer to write data into, and currently just uses an extremely simple approach of indexing into the global buffer. But we could even consider allocating memory there. I'm not super fond of allocating memory directly in this transmit function, since it might be kind of hot. So for the moment, I am sort of preferring a static approach. And then in the system call, we can just chunk it up. Yeah, okay, so we can try to do that. I'm just thinking about how to actually test this, or if there's a way to, I don't know, unit test this somehow. I kind of feel like significant work should not be handled directly in the system call handler function like this. But I'm gonna get to that later. Let's just finish sketching this thing out. Okay, that's why it wasn't being found this. So it's declared here. And we have our system called numbers. Okay. Transmit. Sys network transmit and actually not really done this before, so here we're implementing the user space library. So this is a function. This is like in libc basically, and all of them just use like the generic syscall function, which let's check if it checks the return value. Interesting. So some of these things do. So actually, I'm just going to say yes. I want you to check the return value. This thing should just be regular int. Returns int 32t. Okay. But these other things just do ints. So I think that's fine. Right. And theoretically, this is actually mostly it. I just need to add my work transmit, this network transmit A1, A2, I suppose. But what? And these are just uint 32t's, so I need to cast this to a const char. And this to a size t, I guess. I'm not sure we do that in a lot of other places. Oh, we do that right here. But then it was saying we need to, need to validate the pointer len given by user space. So that's where our assert or check, what? My user mem assert. Yeah, my code completions are not really working super well today. User mem assert though. How does this work again? I would love to be able to jump to definition here. But that's not working. You give it an environment. Virtual address and permissions. Cur-env. So this is an example of how to use it. Cur-env, buffer, len, and permissions. So these are the given permissions to validate against. Okay. Okay, so we've done a very simple system call that exposes this to user space. Okay. This is in the C library. Oh, I need to provide a uint32t. So I need to cast the pointer to a uint32t to pass it into here. And that recompiles a ton of stuff because those are commonly used headers, I suppose. Okay. And now the only thing left is to really just try to call this thing. So we include lib.h. So technically, sys network transmit, and we can just do the same thing we did in the kernel. Something like this. Except instead of this, it's just sys network transmit. Sys network transmit. We don't need to pass this driver thing. All we do, we don't even pass this boolean. All we do is pass some stuff. And just to keep it simpler, so right in the system call, it uses true here, so we're automatically just going to get new packets for everything, and I'm just going to do, I'm just going to do i+1 just to switch it up a little bit, and I'm going to go back to the kernel thing and remove this, so the init is no longer going to produce anything. I will actually just comment this out also. So we're going to run this, and we're just going to see an empty pcap. We're not going to see any pcap, or just a bare plain 24-byte empty pcap. Now we're just going to, we're going to enable this. Recompile. Oh yeah, I can't use this thing anymore. I'm just going to say 32. Okay, so now this thing is not being found. And why would that be? Because I did not okay, I didn't. Wow, some socket prototypes. Syscall.c. And this thing includes, what is syscall.h inc? Right, that's for the syscall numbers. Syscall. And then apparently lib.h is where the actual prototypes go. Oops. Okay. Now this compiles. What's up, Nishant? Yes, I do use ChatGPT, but I try not to. I try to just code otherwise, and then only if I have like serious questions. So now, I guess it's time for a 20-second break. Be right back. Okay. Yeah, let's run it. So what we're going to expect here is that we're going to see a PCAP as we have been seeing, except it is going to be generated by user space. And it's going to start with a 1. We're going to see 64 individual frames also. That looks good to me. So now time to TCP dump that thing. And that looks right. We see, you can see a hex 40 down here. So that's hex 40 individual raw frames that have been transmitted from user space. I'm gonna call that a win.
This is a certified hood classic. This is a certified hood classic.
All right. Yeah, I mean, this is just the most basic form of like a bad system call. It's pretty bad right now. Yeah, it is limited. It's basically limited to 128 bytes at the moment of transmission size. Yeah. So right now it's up to user space to, I guess it would be up to user space right now to chunk up the transmission into appropriate sizes, but we would need to actually expose this Boolean argument for that to work. So that would be another way to solve this too. Push it onto user space. Make user space do the chunking up. Chunk up in the kernel. Okay. So we have a lot of stuff here. Switch to fork. Actually, so in here we have some changes for adding end a packet thing, yeah. This is not really relevant. Okay. I might just amend this into the previous one, actually. Okay. Then the rest of this. So I guess I'll just do the system call part. And yeah, this was necessary because here we just simply pass the global driver. Yeah, I mean, maybe in production, this function even shouldn't, like, it's not really sustainable to have just every single system call be implemented in this one file, so. Yeah, probably we should break these into separate files at some point. Yeah, okay. This thing. Don't need any of this, actually. This can go. This can also go. Oh, shit. And this stuff. All right. Nice. So that was a bit of progress. Slowly. More of the question is, what do we want to do with that system call? It kind of depends on this part. The next part is transmitting packets network server. Now that you have a system call to transmit to the transmit side, it's time to send packets. The output helper environment's goal is to do the following in a loop: accept IPC messages from the core network server and send the packets accompanying these IPC messages to the network device driver system call. These IPCs are sent by the low-level output of this network stack. That's interesting. So I don't know, this like integrates against the network stack and starts calling some JOS specific functions. It allocates the shared memory thing. Does the IPC send here. And then the network server receives these interesting. Beware of the interaction between the device driver, the output environment, and the core network server when there is no more space in the transmit queue. Core network server sends packets to the output environment using IPC. The output environment is suspended due to a send packet system call because the driver has no more buffer space for new packets. The core network server will block, waiting for the output server to accept the IPC call, right? So that kind of all goes back to this diagram. Up here. So they're kind of talking about this output helper environment. So we've done this part. We've done this part so far, the TX ring. We've done the send system call, and so now the next part is this connection here, the output helper environment, which is just a simple loop that receives output IPC and then calls our system call. And this is the one that's going to use the system call that we just implemented, and it's probably going to not want to have all these limitations about chunk sizes and stuff. So yeah, we either put that into a user space library or we just do it all in the kernel. I'm thinking probably just doing it all in here would make sense. Yeah. I guess what does the API look like? You can pass in a buffer, probably a similar kind of interface to reading and writing, where we try to write as much as we can and then return to do arbitrary sized buffers. Return value is what was successfully sent. What happens if TX buffer is full? How do we test, unit test any of this stuff? Yeah. Hawkman, you're about to do lab 6. Any tips? It seems like this is a magnitude more difficult compared to other labs. Yeah, I'm finding it pretty difficult. Any tips? Yeah. I don't know. It's just like kind of hard. Yeah, like I'm trying to keep my documentation kind of close and accessible. There's a lot of different parts of the documentation to have around. There's just a lot of unknowns, and there's very little guidance for this part relative to the other labs. I think my only tip would be to don't panic too close to trying to do the transmits, because I lost a lot of time because of that, because that was causing the Kimu to not like output the PCAP for kind of a dumb reason. So just be careful of that, maybe. There's also just like a lot of decisions. Like this is very open-ended, unlike everything else, and so it's no longer just implementing existing APIs and functions that they have provided. So yeah. So currently, if the transmission buffer is full, we simply drop data and return an error. What would an alternative look like? We could block. That's like another alternative. Alternatively, the call could block. Which is maybe not so nice. Like, as they were saying, we don't want to really block the output environment. So I'm sort of feeling like just simply dropping data. Yeah, I don't know. Otherwise we could like maybe buffer it locally a bit more separately in a separate allocation that the kernel has. I think it's like I'm having a hard time deciding because I just need a bit more maybe context or experience. But I think for sure, yeah, we will need something for breaking up the buffer into chunks. I would also really love to have some way of like unit testing this somehow, but I'm not sure how could we do this? So in general, testing is not very well done in the kernel. Some things, like the one way it is done is at some parts of the kernel we just call some like check functions that like just like run, they ran during just the boot process, and they just like kind of like unit tests. But they kind of interfere with the state of the kernel, and in this case, if we actually ran network unit tests that tried to, for example, transmit some data, do checks on the return codes or stuff like this, that data would actually appear in the end PCAP, which is not great. So I guess in lieu of that, we just can have some user space programs. And that kind of would be the test here. Like, we have some programs that, I don't know, just do some various calls of the system call and check the return value, maybe. Okay. Well, anyway, in that case, that will be for a future time. Hello, Praga this far, and Ver. Thanks for joining. I'm about to end the stream, I think. I gotta go, but this was a pretty good one. We made some decent progress and made it through at least a basic version of exercise 7, although we have some more work to do. So I'm gonna call it here. Thanks a lot for watching, everyone. Hope you have a good day. I'm gonna post my Discord link. Please like and subscribe if you enjoy this stuff, and I'll be back here next week. All right, have a nice one. Bye.